Welcome everybody. In this presentation we'll cover motion and terms that we might use to describe motion are speed, velocity, and acceleration. Speed and velocity are terms that might be used interchangeably by the layperson, but in physics we distinguish the two quantities. And when it comes to types of motion, two very simple types would naturally be a straight line motion or circular motion. But of course, there are many types of motion. For example, elliptical. Mercury partakes in an elliptical journey around the sun. Here's the distinction between speed and velocity. When you're driving, you might say you're traveling, say, 50 miles per hour, or if you're in another country, maybe 80 kilometers per hour. With velocity, you would say the same thing, that you're traveling 80 kilometers per hour, but you attack on a direction. You attack on a direction. In other words, velocity is speed plus direction. Velocity is speed plus direction. Furthermore, whenever you have a quantity that includes direction, what you have is a vector. Whereas if you have a quantity that doesn't include direction, we call that a scalar. For this reason, speed is a scalar and velocity is a vector quantity. Another example of a scalar quantity would be mass, for example, 50 kilograms. An example of a vector would be force. For example, let's say that I weigh 150 pounds and I'm standing up. The reason why force or my weight has a direction is because the ground is receiving my weight. Or in other words, my force or my weight is acting downwards. So keep that in mind. Mass is a scalar quantity with no direction, but force has a direction. Another example of a scalar quantity would be temperature. You just say that the temperature is, say, 70 degrees Fahrenheit. You don't give a direction. Another example of scalar would be energy. Another example of scalar would be pressure. Another example of a vector quantity that we'll see later is acceleration. The rate of change in velocity per unit time. Here are examples of vectors. You can see that the length of the arrow determines or conveys the size of the vector. So for example, the vector on the right is twice the size of the vector on the left, and notice its value is twice as much. Furthermore, it's a vector because it has direction. For this reason, we would say that for this vector quantity, the speed is 40 kilometers per hour, but the vector is 40 kilometers per hour to the right. Whereas the one below is a vector quantity of negative 40 kilometers per hour to the left. That's the velocity. Here we have cars and a pedestrian moving along. And notice our pedestrian has a short arrow, which conveys the fact that she's walking very slowly compared to the car, which has a long arrow, which conveys that its velocity is much larger in magnitude. Whenever you hear that expression, velocity in magnitude, we're just talking about the speed. Okay. Or in other words, whenever someone says a magnitude, you're just talking about the scalar portion. The scalar portion. Here's the definition of average speed. And no surprise, average speed is distance divided by time. And typically, whenever you see an average quantity, people like to put a bar on top. You may or may not see that written. And the average speed is distance over time. The distance is the actual path traveled. Here we have a speedometer, and you can see the person is traveling 50 miles per hour. Or if you're maybe in another country that follows another set of units, you would say you're traveling 80 kilometers per hour. This is known as the instantaneous speed, the speed at which you're going at a particular point in time. Now, if you stay moving at 50 miles per hour, then your average speed and your instantaneous speed will be the same for that duration. Here we have displacement given, and I think the picture does a better job than the words. Here we see the distinction between displacement and distance. So suppose you're traveling from here to here, from home to the college. The distance is the actual path traveled, in length. So it's like you take an imaginary string, you lay it down, you stretch it out, and you can hence have the distance traveled. But displacement is the length of the um, imaginary arrow that connects your origin to your destination. So again, displacement is the length of the imaginary arrow that connects your origin to your final destination. When talking about average speed, you would calculate the total distance traveled divided by the time it took to traverse that particular path, assuming you're traveling on this bottom half leg of the journey here. And if you were to calculate velocity, let's see, what equation would you use then? Well, let's go back a slide here. The average velocity is displacement over total travel time. So keep that difference in mind. Average velocity and average speed, they have a different numerator. Here's an example. Describe the speed of the car above. You traverse 80 meters in 4 seconds, and therefore the average velocity is just 80 over 4. So your speed is 20 meters per second, or your average velocity is 20 meters per second to the right. Here we're asked how far would the car travel in 10 seconds? How far would the car travel in 10 seconds? Well, here you have to do some math. Uh, you know the equation for average speed is distance over time, but the question is asking how far. In other words, you want to solve for d here. And to solve for d, I need to get d by itself, so I just take the t and throw it up top. In which case, I'm looking for this calculation here to be solved. And how far the car travels in 10 seconds and 20 meters per second that we calculated on the previous slide, then it's just simply the 20 times the 10. So we travel 200, or the car travels 200 meters. Here we see a picture of the Earth going around the sun, and we're told that it takes about 8 minutes for sunlight to get to us, 8 minutes. and the distance is 93 million miles here. And notice that it is a wave. Light is a wave. So actually, light has a duality. It can be a wave or a particle. It just depends upon the context. And again, if you want to convince yourself that it's a wave, like I mentioned in lecture, just take a slice of pizza, stick it in the microwave, and you'll see these bumps that arise in the cheese, and hence that's your crust there. Okay, so you can just measure the crust to crust distance on your cheese pizza, which would be, I think it'll come out to on the order of somewhere between 1 and 10 centimeters, and you can just then multiply it by your frequency of your oven, microwave oven, and get the speed of light there. Or you can also use a chocolate bar. Okay, and the light we receive from the sun, uh, uh, it didn't just leave the surface of the sun, it left the interior of the sun. And amazingly, the time it took for that light to get to the surface of the sun was at least 100,000 years. So this light that we're getting was created at a time before modern humans walked the earth. Here we're asked, what's the average speed in miles per hour of the earth revolving around the sun? Okay, so this is just distance over time. But before I can do distance over time, I need to know what is the time and what is the distance. And I'll do it for 1 year. 1 year. Okay, so the time is 365 days, for which I want to calculate the average speed. And I'll go ahead and convert it to hours. And remember that there are 24 hours in a day. So this is the conversion right here. 365 times 24 is this guy here. And the distance for the Earth to go around the sun is 2 pi r. And there's 2 pi, and r is just the 93 million miles here. And here they just go ahead and do the calculation. They just plug and chug. Next we come to acceleration. And acceleration is the rate and change in velocity per unit time. The rate and change in velocity per unit time. An example of acceleration is you could be driving along the road and press on the accelerator, in which case your speed would be changing. Another example of acceleration is you might go around a turn while driving. When you take that turn, even though your speed might be the same, because your direction is changing, we say that your velocity is changing, and hence you are undergoing an acceleration. Keep that in mind. To have an acceleration, you have to have one or both quantities changing. That is speed and or direction. Or in short, you can just say velocity is changing. And we'll see an example. Here's the equation. Average acceleration is just change in velocity over the duration. And physicists like to use this subscript F to mean final and O to mean original. So final minus initial. And the units of acceleration are, of course, the velocity units, or the speed units divided by time. So you get meters per second squared. The way you can interpret this is as for every 1 second that elapses, the acceleration here increases by, say, 1 meter per second. If I had a minus sign in front, the interpretation would be that for every second that elapses, the speed decreases by 1 meter per second. Here's an example. A race car starting from rest accelerates uniformly along a straight track. A race car accelerates, and we're told the speed, the final speed, and the duration. All right, so we have the final speed, the duration, and we're told that the initial speed is 0 because the race car starts from rest, which means we're all set. We can just go ahead and jump and start, almost, I guess not exactly yet, because if we want our answer to be in meters, we need to do some conversion. So here they gave us kilometers per hour, so let's just convert this 90 kilometers per hour to meters per second, and they do that here. And if we go to our friend Google, we find that this is the conversion here. To go from kilometers per hour to meters per second. And then, so we see that 90 kilometers per hour is just 25 meters per second. And hence, coming to the last line, we can just go ahead and use the acceleration equation. Change in velocity over time. The final velocity is this guy, 25. We start from rest, so V0 is 0, duration is 7, plug and chug, 3.57 meters per second squared. And here we just have a magnitude. We're not given the direction, but we could say it's to the east, in which case we would just tack on the word east to make then acceleration a vector quantity, or written as a vector quantity. But again, if you just write the number with the units, we call that the magnitude. And since this is the equation for acceleration, you can do some manipulation here algebraically and write it this way here. So the final speed is the initial speed plus the change in speed due to acceleration. Again, the final speed is just your initial speed plus some additional speed due to acceleration. This equation is very nice because you can also use it to describe a ball that is dropped from, say, a building. You drop the ball and its initial speed is 0, and over some time, t, that it takes to hit the ground, the ball accelerates due to gravity. And right before it hits the ground, it has acquired some final speed. There is a caveat to this equation. It assumes that our acceleration is constant. If acceleration was not constant, this equation would not be correct. You'd have to tack on an additional term, which engineers call a jerk. Here's another example. If the car in the preceding example continues to accelerate at the same rate for 3 more seconds, the car accelerates at the same rate for 3 more seconds, what will be the final speed? What will be the final speed? Well, so we know that the acceleration from the previous slide is 3.57 meters per second squared. We found that in the not the previous slide, but the one before that. So here it is right here. We did this already. And so we use that acceleration, but now we're told the total time is 10 seconds. So in the problem, they said it's 3 more seconds, which means you're adding 3 to the previous 7, so it becomes 10 seconds. And again, you're starting from 0, initial speed, so you use the same equation as that we saw on the previous slide, where final velocity is initial velocity plus acceleration times time, and plug and chug, you get 35.7 meters per second. Here's a nice illustration of distinguishing acceleration and deceleration. I notice on the left here the car accelerates from 10 kilometers per hour to 20 kilometers per hour to the right. And hence, for that reason, the acceleration vector is facing to the right. But here in the right panel, notice that the car decelerates from 30 down to 0 kilometers per hour. And since the car is slowing down to the right, that means the acceleration is actually to the left, right? Since the car is decelerating to the right, that means that the car is actually accelerating to the left. You can also write this out. Notice that that statement, accelerate to the right, is the same as saying decelerate to the left. So all I did was negate each part of the sentence. Okay. Now, similarly, for the left panel, even though no one would do it, or people would consider us weird for saying it, for that left panel, you could say that the car is accelerating to the right, or you could say the car is decelerating to the left. Same thing. Here's a nice illustration about what I was telling you in regards to the um, um, the occurrences of acceleration. That is, either a change in speed or direction or both, or in short, a change in velocity. So here you have a race car going around a turn here, and notice that at one moment his velocity vector might be facing in this direction, and then another moment later her velocity vector is facing slightly downwards. So in that fraction of a time, that change in velocity is going to be facing in this direction. So at one moment the velocity is this way, a fraction of a second is this way, the change in velocity in that duration is down. And notice that the change in velocity faces towards the center of the track. This means that since acceleration is proportional to the change in velocity, it also faces towards the center of the track. Whenever you go around a turn, your acceleration vector is facing towards the center of this imaginary circle around which you're going. Furthermore, you can imagine that the car is moving at constant speed. So V1 and V2 might have the same speed, but they have different directions. And those different directions give rise to a change in velocity and hence an acceleration. Or the car could be both changing direction and changing speed. Notice also here they use the subscript C's. This stands for centripetal acceleration. Centripetal acceleration. Centripetal just means center seeking because the acceleration vector is facing towards the center of this imaginary circle around which our race car is traversing. And the reason why the race car is able to go around this turn is because of friction between the road and the race car's tires. Without that friction, of course, whenever the driver tries to turn, the wheels will turn, but the car is going to keep going straight, right? Or if you take this position here, though maybe the race car driver turns the wheels to the right, because of no friction, the car would just simply go straight and hit the wall. But it's the friction that allows the car to make this turn here. Here's the equation for centripetal acceleration. It's simply the speed squared divided by the radius of the imaginary circle around which the object is traversing. Okay, so again, centripetal acceleration equation is the formula for the acceleration undergone by the object when traversing a circular path. And Now, this fits our intuition because you can imagine that if you're going around a tighter turn, the radius of your imaginary circle is smaller because you're making a tighter turn. Well, if my radius is smaller according to the formula, then I have a larger magnitude in my acceleration. Remember, a smaller denominator, a tighter turn means a larger overall result. That fits my experience because when I take tighter turns, I feel a greater force, right? The side of my body would hit the side of the car, right, if I make a very tight turn. In other words, you can think of acceleration as suggesting force. Okay, whenever you have an acceleration, you always have a force involved. In the previous slide, it was the contact between the tires and the road that supplied the frictional force, and hence the centripetal acceleration. Here's an example. Determine the magnitude of the centripetal acceleration of a car going 12 meters per second in a circle of a radius 50 meters. Here the speed doesn't change, it's only the direction, but still you get an acceleration. And we just plug in chug, so 12 squared is 144 divided by 50, so we get an acceleration of 3 meters per second squared. Again, this is just a magnitude. And if we wanted to make it a vector, we would have to write facing towards the center of our circle, right? Here you're given another example in regards to the Earth. Compute the centripetal acceleration for the Earth. Well, here's a radius of the Earth in meters, 150 billion meters. And the speed of the Earth is here, 30 kilometers per second. All right, so we stick in 30 kilometers per second. We square it. That's the speed squared. We divide it by the radius of the turn. And we get this very tiny number, 0.006 meters per second squared. Or you can say 6 millimeters per second squared. So that's the reason why here on Earth, we don't feel the Earth's centripetal acceleration because it's so small. But you can imagine if it was a lot larger, we would definitely notice it. In this slide, we have what's called projectile motion. And notice on the left here, maybe someone shoots a cannon or throws a ball. It partakes in what appears to be an upside down parabolic trajectory. And the nice thing about this trajectory is you can divide it up into two pieces. You can make it both a vertical piece and a horizontal piece. So so consider half the parabolic trajectory up to the top of the motion. Well, that curved path can be thought of as made up of two pieces. The vertical piece, taking the ball upwards, and the horizontal piece, taking the ball to the right. And then for the second half, well, just a similar thing. Again, a vertical leg for going down, and then again, the horizontal leg. Now notice that gravity, since it acts downwards, it doesn't affect the horizontal speed. This means that when illustrating the horizontal speed of the object, you would just keep the length of the arrow the same. This Vx0 means the speed of the object in the x direction. The speed of the object in the x direction. And the reason for the 0 is because the speed of the object in the x direction is the same as it was initially. So remember, 0 just means original. But notice for the vertical speed, the initial vertical speed, which is written as v subscript y0, it decreases as the ball goes up. and it comes to a halt, which makes sense because we know that it comes to a halt here, but then it picks up speed going down. So the arrow decreases in length, the vector decreases, but then afterwards it increases coming down. You might recall Pythagoras' theorem, a squared plus b squared is c squared. Well, here you can do the same thing. You can draw a right triangle and say that the hypotenuse v0 squared is the sum of the square of the legs. V0 squared would be Vy0 squared plus Vx0 squared. And here's a quarterback illustrating the previous illustration. And notice the horizontal speed stays the same, Vx here. But notice the vertical speed changes direction. Okay. And notice also the symmetry in the path. And notice the vertical speed is 0 here, but it still has a horizontal speed here. And that is the end of the slides. And let me know if you have any questions. Thank you.